So hello again from me. So as Robert already mentioned, I'm going to present some of the upcoming features in the next 0.10 release. But I'm afraid Robert, he already mentioned most of the stuff, so the high availability, the monitoring, and he mentioned this also. I'm going to do a demo of on my laptop. I'm going to start a fake cluster and then do a demo of a running streaming job with fault tolerance. And also, these are just the highlights. I think there's a lot of other bugs being fixed, other features, but these are the interesting bits for now, at least. And also, please ask questions if you have them. So this is going to be very high level. I'm going to explain the main concepts, but then please ask questions about any stuff about after any of these high-level introductions. So the first bit is high availability. So first, the question is, why would we need high availability, or what is this exactly? So this is the current status. So what you have is does this work? You have one job manager, and you have these task managers, so the master and the workers. And now what happens if the job manager goes down? Then what you do, you basically panic because the whole system is going down, your job doesn't run anymore, you don't get any more results, you're basically screwed. So that's why you need, or why you want, high availability, as we call it. So here the idea is that you, again, as you see, we have master and task managers, but then you have, additionally, you have a standby job manager. So here in this example I have one standby job manager, but you can also have more standby job managers if you want to be extra high available. And these job managers, they communicate with Apache Zookeeper. So I don't know if enough people know about Zookeeper, but it's basically, it's a system for doing stuff in a consistent way and storing stuff in a reliable and consistent way, basically. So what happens now, if the job manager goes down, then the other job manager just connects to Zookeeper, retrieves some stuff from there to take over from the old job manager, and the task managers connect to the new job manager, and the program just keeps going, hopefully. That's the basic idea behind the new high availability feature. And so some of the details, so as I said, we use Zookeeper for this, and it's basically used for leader selection. So when you have multiple standby job managers, there has to be some protocol for who picks up as the new leader, and then how the task managers connect to this, and so on. And it's used to store the data flow graph of the running job, and also some metadata about checkpointing. So if you have a streaming job, if you want to have fault tolerance, you do checkpointing, and this also needs to be stored in some consistent and reliable way. That's what this is for. This is actually the last slide about high availability. So if you have questions about that now's a good time to ask them. Yes?
How long does it take to switch the job manager to the new one?
Repeat the question, please.
How long does it take?
I have to repeat it. So the question was how long it takes for the job manager to take over, and the answer is I don't know, actually. But I think Till, this guy, maybe he knows, because he's working on this feature. I'm not working on this feature, but maybe he has some answers for this.
Well, it depends how quick Zookeeper can tell you, basically.
So he said it depends on how quick Zookeeper can tell you. I'm just repeating for the recording man. So yes, please.
I think for most of these things, the longest delay is usually figuring out that something has failed, actually. So you don't immediately recognize if something has failed. You usually recognize it if after a while certain responses don't come anymore. For example, Jan keeps monitoring processes every so many seconds, and it sees the process is gone and reports it. It takes a few seconds. It usually takes longer than these Zookeeper delays. So.
Yeah, I'm not repeating this one. So
how big is the data that you have to store in Zookeeper to have this checkpoint metadata?
So the data that is kept in Zookeeper is just some handles to the checkpoint. So what we have an abstraction For state, we call them state handles, and then, for example, if the state is actually stored in HDFS, then the state handle that is stored in Zookeeper is only the ID basically of the checkpoint and where to get the actual content of this checkpoint. So it's small data, not the actual checkpoint data. Yes, please?
How large is the overhead introduced by keeping multiple job managers at standby?
So basically you have to have additional machines running basically, or additional jobs in Yarn.
I mean, will I notice during program execution, will it take longer if I execute with this new feature or the old one?
No, the standby job managers, they don't affect the actual performance of a running job. No. Yes, please.
And as a small maybe what you usually have to do is you have to do a round trip with Zookeeper to figure out who's the leader when you submit a program. So when you actually throw it into the cluster, you may see like a slight delay. But once it's running, it's actually done in Zookeeper. So it's not fair. I think that's what Aljoscha is referring to.
Yeah, again, not. So. Do you have more questions? We can also ask any of us after this. So we're here, there's beer, so we have time if you're interested. So the next thing, Robert already mentioned this, is live monitoring. So a bit of background. So in Flink, you can, like in Hadoop, you can have these accumulators or counters where you have some running statistics of a job, and the status before the work we're doing here is that the accumulator results are available after a job has finished. This is because of this basically how it was in Hadoop. And in batch jobs, you have a job that runs, and then afterwards you want to know the accumulators. But now, if you have a streaming job, this is basically running forever, and then you never finish. So you want to have these accumulators updated live as the streaming job is running, and you want to have statistics on how many bytes the operators process, how many elements they see, how much they emit, and so on. So that is why this is an important feature for streaming jobs. And as I said before, only available after the job is finished, but now what we have is that the accumulators are live, updated while the job is running. And we added some system accumulators, as I said, about the number of bytes processed and the number of elements processed and so on. Yes, please.
Can you choose the frequency in which the accumulators are updated? Or are the accumulators, or is to get the information from the accumulators, do you have to make a request to get the information, or just do the accumulators send their status updates and put them in some kind of system?
There again, I have to put the question to this guy because he implemented the updated accumulator feature.
At the moment, because the accumulators are exposed in the job manager web interface or elsewhere, and the interval at which they are reported is not yet configurable. It's just updated usually with the heartbeat signal of the task manager, which is like 5 seconds default. But yeah, once we integrate it with the web interface, we will also make it configurable, which is not hard to do.
And I'm going to show this one again. So this is the fancy new Node.js, AngularJS dashboard interface. And once this is running, then you will get the accumulators live in the web interface. So that's the last slide for this topic. Next bit is timestamps, watermarks, and what else is going along with this stuff. So I'm going to explain what this is, but first we need some introductory stuff. So what is this about? So in streaming, the problem is that you have, or you assume that you basically have an infinite stream of arriving elements, and when you want to do some operations that perform aggregations on the stream, you need to, let's say, discretize the stream into windows. So you say, for example, discretize it into windows of 10 minutes, and then on these 10 minutes, you can collect the elements in these 10 minutes, and then perform some aggregation operation on these. And the problem is now, let's say you have a stream of incoming elements, and the element, it has a timestamp, which is maybe the time at which the user clicked something in a website or something. This could be the timestamp. And then it has a payload, which is just some random data. And now what you have, the elements flow into the window operator, and then the operator should perform something to emit these windows or do operations on windows. And the question here is, which elements are inside these windows? So how do you group these elements with the timestamps into windows to perform operations on the windows? And there are basically two ways of doing this. So one is you do windowing based on processing time. So what this basically means is the elements that arrive first, or basically you don't look at the timestamp, but you assign them a timestamp when they enter the operator, which is the current system time. So what then happens is you get these windows. So these here are the first three elements. These are the next. So the elements are put in the windows which don't really correspond to this timestamp attribute. But this is maybe easier to do, or most systems do this because it's easy to implement. But there's another way to do it, which is you do windowing based on the actual event time in these events. So if you look now, what we have here is we have a window of these three elements, and they arrived in a completely different order here. But the logical timestamp that they have says that they should be in this window together. And then also you have these elements, which also arrive interleaved with the other elements. But again, the timestamp values are close. They should be put in the same window. So the question is now, how do you know basically when you can process these event time windows? Because as you have seen, these windows, they can arrive in a completely arbitrary order, which doesn't correspond to the actual timestamps that they have. So when do you know if all the elements for a certain span of time have arrived, basically? That's the problem. And the solution is watermarks. So this, the concept of watermarks, I think the name was introduced in a paper by Google about mill wheel, which is there. They popularized it in this paper about their streaming system, but it goes back to previous mentions in other papers, and sometimes the concept is called punctuation, so it has some history. But this is the most recent mentioning of this name, and also the most prominent system, I would say, because if you know the Google Data Flow API and their system, they also use watermarks to keep track of when to process elements. So basically, how watermarks work is, this is a source, and it emits elements, and this is the stream of elements. And as you can see, the timestamps, they are basically not in order of their timestamps, or the elements are not in order of their timestamps. So what we do is, at specific points, you emit watermarks, and they are intermixed in the stream, basically. So at this point here, we have watermark 4, and what this watermark says is that once an operator sees this watermark, it is guaranteed that no element with a lower timestamp than the watermark timestamp can arrive. As you see, after this watermarks, there's no element with a lower timestamp than 4. But we cannot say yet anything about, for example, these elements or stuff, because there arrive elements with lower timestamps. And then once you have the watermark 8, there's no element with a lower watermark. And then watermark 15, there's nothing lower than the 15. And what the operators now do, they have to buffer the elements somehow and store their timestamps. And then they wait for these watermarks. And when they get a watermark, they can process the elements for which they know that, or for which the watermark tells the operator that no element with an earlier timestamp can arrive in the future. And then they can process these windows with these watermarks, and then once an operator knows that it itself cannot emit any elements with a certain timestamp, then it itself emits a watermark, so that operations in the streaming topology downstream from the windowing operator, for example, they can also do processing based on these watermarks. That's the basic idea. So this we have now in the system, and now we're working on providing actual windowing operators that can also use these timestamps. So that's, I know it's a bit scary and tricky, but please, if you have any questions. Yes?
Is this specific to timestamps, or could it also be another value that you use for watermarks?
So you want to have watermarks for other values? Or what do you mean?
So maybe temperature, what's it, I don't know.
No, I think it could be implemented, but right now it's only, or we only use it for time, because it's a well-defined problem that you have time and that you want to do windowing based on time. Because on temperature, then the temperature would have to be monotonously rising for it to make sense, because timestamps also have to be constantly rising, because otherwise you couldn't ever emit any watermarks. So I don't know if it would work for something like temperature, which I guess would be fluctuating.
I couldn't think of a use case.
Yeah, okay, that's, no. Yeah, maybe it makes sense, but I don't, off the top of my head, I don't know any case where it would also make sense. Yes?
Where do you know from when you can emit such a watermark? So basically, the timestamp source can be any source, or maybe I'm just flushing like historical data in addition to live data, and then, so how do you know that you can be sure that there is no other point?
Yeah, yes. The question, yes. So the question is, how do you know when the sources can emit the watermarks? And the answer is that it's a tricky question. But for example, if you have a system that puts these timestamps into elements while it creates them and puts them in a log, which has increasing timestamps, then the source that is reading from these can know that the timestamps in a log cannot become lower again, and then the source can emit the timestamps. Or for example, if you we call this ingress time, so when you read an element into the streaming system and then you assign it the current time as the timestamp, then you also know that you can emit watermarks at a specific interval and so on. But this is tricky, yes, and you also then, sometimes the watermark is not 100% guarantee, but just some heuristic, and then you need to have a way for example, dealing with elements that arrive after the watermark, which theoretically should not happen, but might happen in a real world system.
There's an API that we can say like, watermark happened now, or is this all done automatically?
No, it's not done automatically, no.
Okay,
So
we
for-
need to explicitly say from our data source.
Yes, so-
Now's the watermark.
Yeah, so for example, the source has to be implemented in a way that it also emits these watermarks, because it should know what happens with these timestamps and when it can emit these.
So imagine you have a distributed source, and you know that every minute, hour, whatever, you synchronize clocks between these distributed systems, the distributed nodes which can all emit data to this streaming job. Then they have agreed that about the minimum time that they all have seen, and they can emit this is what we accept. So it's depending highly from the source.
Yes, yeah.
Now, we could say we have a guarantee that clocks never perform more than X seconds, and then you could always implement a timestamp passed after this epsilon has passed.
Yeah.
Thank you. Yes, please.
Is it a problem, I'm not sure about the system design, but could it happen that watermarks get mixed up, that they don't arrive in order?
No, when a source, so the assumption is that the source doesn't emit watermarks that are lower than previous watermarks, then it should not happen that they mix up. So the thing is, if you have several sources and they emit watermarks, and then they can be out of step, so one can be faster, one can be slower, but then what the system does is that at an operator, the watermark that the operator gets is the minimum of all the incoming watermarks. So then this is how it puts them in sync again. But it should not happen that the watermarks themselves go out of order. They must also be constantly increasing. Any further questions?
So why do I care about order?
Why should you? If
I introduce the watermarks, let's say I will add some latency. So I have to, so what I see there is I have to trade my latency with the order. So I gain order, I lose the latency.
yes,
So can you give us some examples of why would they do that?
it depends on the use case you have. So if you want to have minimum latency, then you don't care about the timestamp, and then you do use processing time, which gives you approximate results. But if you want to be absolutely sure about what the windows happen, or when the windows happen, then you would use the watermarks. And the impact is actually not too high from the watermarks.
Given that the watermarks are going to behave well, but if my application semantics demand some order that might come after half an hour and they never send the watermark from the source, then how is the system going to handle the back pressure? Is there a way to make sure that you persist tuples while waiting, for instance?
Yes. So while it's waiting, the system just keeps buffering the stuff. Or if it's some running aggregate, then it's keeps summing up the aggregate. But if you require the semantics that you have absolute correctness, then there's no other way than waiting for the last element to arrive for this window, if this is a requirement.
I think there's also a second answer to that, and that is, I think what a lot of people think right now when they think of stream processing is some of these like ultra low latency things. There's fraud detection, thing running a test or answer like architecture less than 200 milliseconds to figure this out, right? But this is really not the only way, the only thing that stream processing can cover. You can also basically do a lot of processing of historic data together with newly arriving data and so on. It's a more general paradigm that can actually sort of subsume the mesh paradigm. And if you think about a way a lot of people who've used Kafka, for example, is to buffer streams for a very long time, let's say for a week, and then they run some stuff over it, they maybe change the program, run over it again, maybe change some assumptions in the history, reprocess the stream. And if you do this based on what basically every other system does on processing time, then every time you run it, you get a different result, right? Because the time is different when you run it, right? If you do it based on timestamps, you actually can repeat the results that you have. So it actually makes streaming computation repeatable, which is, I think, in itself extremely valuable for many applications.
So the idea here is that you're not forced to use watermarks, right? This is an option. You can use if your use case, for instance.
Any more questions about this? So then let's move on to fault tolerance. So the thing is, this is actually not a new upcoming feature, but we already introduced fault tolerance in the 09 release. I don't think we properly talked about it here or in some other places, maybe yes, but it's an interesting feature and I'm going to have a little demo about it. But first, the question is, what is fault tolerance, or what different paradigms are there, or what can you do basically? So there's one paradigm, basically, I would say, called at least once. So there you want to have the property that every element that your system receives should at least be processed in your topology once, but it can happen several times. So if you don't care, or if your operation is idempotent or something, then you only need exactly once, and this is easier to do than more costly fault tolerance principles. But this is one way of doing it. And then there's a stricter guarantee or stricter idea of fault tolerance, which is exactly once. And there you want to have it that logically every element that you're streaming topology receives is only processed exactly once, or is only reflected, let's say, in the state or the output once. So practically, the system might still process the element several times, but the system needs to guarantee somehow that the external view or the logical view of what happens is that every element is only processed once. And there are several solutions for this. So one is discretized streams or mini batches. So the idea here is that your system receives the input elements, puts them in a buffer, and when the buffer is full, or when some other criterion triggers or something, then you start basically a batch job and process this buffer. And when the batch job finishes, then you have the final result. Everything is good. When the batch job fails, you just completely restart the batch job and throw away the earlier results. And then this result is also good. So in this way, you use the fact that you have a well-working batch system to provide fault tolerance for you. But this might come at the cost of some of latency issues, and also it makes some stuff problematic, let's say. We can discuss stuff later offline after this talk. Then the other idea is what this mill wheel, what I mentioned earlier, does. It basically, it has a transactional state store, and basically the processing of the element and the update of the element become one transaction, and only when everything, the processing of the element and the state update is gone through, then this is committed to the external state. So if you have this, and if you have a very high throughput transactional store, which Google, I assume, has, because they are doing this, then this can give you good performance and good semantics, and it works well. And another idea is what Flink is using. It's a variant of the Chandy-Lamport distributed snapshot algorithm, which I'm going to explain next. So this is the Lamport from LaTeX also, but he did a lot of work in distributed systems. That's why he's quite prominent in this field also. And that's an interesting algorithm that we are using. Now this looks complicated at first, but so let's break this down. What we have here is the yellow dots. They are the operators of the streaming topology. That's some source. These are operators in between operators, and these at the end are sinks. That's the master node. Here's what I mentioned, the metadata about the checkpoints, and we have some state backend, which could be HDFS or something else. And for these sources, we have the reading positions in the input stream. So this would, for example, be in Kafka, this would be the read position, or in some other input system, some state about the source that can be used to roll back the source to some previous state, basically. So we have this state, and then what happens when the master decides that it should do a checkpoint, then it sends to the sources a message that they should start checkpoints. And what the sources then do is, this is somewhat similar to the watermarks I mentioned earlier, but only rough similarity. So what the sources do, they're these very small, these dotted lines. So they emit these checkpoint barriers. And what these checkpoint barriers do, they travel down the stream, and when operators receive checkpoint barriers from all the upstream operations, they know that they themselves should do a checkpoint. So we're going to walk through this step by step. So the next position is that the sources, they actually did their checkpoints, they emitted the barriers, and they updated the metadata state in the master. So if you look very closely, I'm afraid, but you have to trust me, these numbers here are basically the read positions from the earlier slide. This is the state in the sources where they are from reading at this checkpoint position. And then what you see here, the operators receive these barriers from all the different source inputs. Then they also write some state to the state backend. And then when they're finished, emit barriers themselves, and then store the handle to the state in the master node. And then when the operators also forward these checkpoint barriers, and then when they arrive at the sinks, they also acknowledge this to the master that the sinks themselves receive the checkpoint barriers. And at this point, we can be sure that all the operators in the stream receive the checkpoint barriers, checkpointed their state, push this to the meta store in the master, and then we know that we have a consistent checkpoint at this specific checkpoint interval. So, again, quite complicated, but please, you can ask questions now. Yes, please.
So this would be a naive question, but this feels like a distributed transaction, which you said was a different approach. So
what I meant, so earlier you were talking about the mill wheel. Yeah. So the question was, this looks like a distributed transaction, and it is in a way, but what I was talking about earlier, mill wheel is, so here the complete topology of the stream is looked at, but what in mill wheel happens, this only works locally on one instance of an operation. So the transaction I was talking about was at an operator that the processing of the element and the update of the state and the emission of the result of this processing is one transaction. But looked in separation in each operator, we have these transactional updates. But what this does is the checkpoint barriers propagate through the stream, and then only when the operators receive these barriers do they do checkpoints. But in between, if no checkpoint barriers come, if no checkpoints happen, the operations, they just keep processing stuff and keep updating their states, but they don't do any transactions or don't store any state in a state backup. That's one of the, or that's the characteristic of this. Yes, please?
So we indicate what actually what kind of state is stored in the state backend. So what's S1 and S2? Is this like the actual data, or is this metadata?
This is the actual data. So the master, this stores the metadata, which is basically a handle to the state. And then in the actual state backend, this can store arbitrary state that the actual values, yes. So for example, if you have a counting operator that is stateful, then it would store the count or something like this.
What would be a good technique to store them, like HDFS or some distributed database?
So currently we have HDFS, but I think we're also looking into other backends. So we have made this state backend very flexible so that we can add additional variants of this. But right now you can store it on in local file system on the machine that the operator is running on, or in HDFS. Low latency, because the normal processing of the elements isn't impacted by the checkpoints. And there are some proofs that this algorithm actually produces a consistent state after these things receive these barriers, so this gives us correctness. And it also gives us high throughput, because I didn't mention this before, but these checkpoint barriers or the checkpoint intervals, they're configurable. So if you want to have very highly granular state backups, you set the checkpoint interval very low, but then of course your throughput is not as good. But if you only want to do very coarse checkpoints, then you set a higher interval and then you get higher throughput. And one very good point is that it separates the logic from the recovery. So in this mini batches approach I mentioned earlier, the system becomes very dependent on how big these mini batches get. And you are constrained by the size of these mini batches, and they might not correspond to actual window sizes that you might want to have. But here the recovery and the windowing and everything is disconnected. So each of them can work correctly of course, the latency and throughput differ if you turn some knobs, but it's separate and not connected to buffer sizes or growing buffers or stuff like that. So that's actually the last slide before I'm going to show a little demo of the checkpointed state and recovery and so on. So if you have questions, please ask now or later. There's a pause after this, so we also have time.